Hello, Math World, and welcome back to IzoMath. Today we're going to talk about the law of cosines and some interesting proofs of how we come about using the law of cosines. So here's an example we're going to start off with. If I'm given this triangle here, triangle ABC right here, I've shown before in previous videos that we can find out this h value, and more importantly, we can find out that h value, but we know that h value on this smaller triangle here, I know essentially that the sine of that big C is going to be equivalent to my opposite over adjacent. In this case is going to be h over a. And if I want to solve for that height here, or that h value, I know I could multiply both sides by a. I'm left with a sine of big C is equal to h. So I can say that this side up and down here, so that means this h value here is essentially nothing more than a sine of big C. And similarly, if I want to try to solve for this t value right here, I can see that using this angle C here, I can see that the cosine of big C is going to be equivalent to my adjacent over my hypotenuse, which is in this case is t over a. And again, rewriting that guy, that is nothing more than a cosine of big C is equivalent to t. So I can see that this t value is nothing more than this, a cosine of big C. So that again, that's that segment from there to there, and then I have the height of the triangle here is from there to there. Now looking at this r value right here, I can see that the r runs from here to here. Essentially, it is the length of b. This r value is the length of b minus this value right here. So my r can also be written as simply, so my r value can be described as r is nothing more than the entire length b minus my t length, which is essentially also can be written as a cosine of c. So this r value right here is going to be b minus a cosine of c. Okay, so the big overwhelming question is, why is this important? Well, now I'm actually able to solve for the c value, knowing that this value of r and this value of h. Why? Because I have a right triangle. I have a right triangle. We know when I have a right triangle that this side length right here squared plus this side length squared is equivalent to the hypotenuse squared. So I know that my c value squared is essentially equivalent to the r squared plus my h squared. But using the rewritten values that I have, we can come up with c squared is going to be equivalent to my b minus a cosine of c quantity squared plus my h value, which is a sine of big C quantity squared. So rewriting this, and I can get to the next step, which is this. So this now becomes, squaring this quantity is b squared minus 2ab cosine of c plus a squared cosine squared of c, and squaring the other quantity, which is right here, the a sine c, gives me a squared sine squared of c. And furthermore, that leaves me with this. Seeing that these two values have both an a squared in front of them, I'm left with, I can factor out an a squared out of those two values, leaving me with this value plus a b squared minus a 2ab cosine of c. And as we remember from previous sections, cosine c squared plus sine c squared is nothing more than a value of 1 plus b squared minus 2ab cosine of c. So my final answer looks like this. C squared is equal to a squared plus b squared minus 2ab cosine of c. That helps me find that c length of my triangle. And this is called the law of cosines. So we've shown that c squared equals a squared plus b squared minus 2ab cosine c. Remember, these are triangles. These are not right triangles. So this is how I go about solving this. And it can also be shown similarly that if I solve for the other side length, and this say a, I could come up with very similar. So be a squared would be equal to b squared plus c squared minus 2bc cosine of big angle A. Or if I had to solve for the side B, my B side would be B squared is equivalent to A squared plus C squared minus 2AC cosine of big B. So these three properties are all laws of cosines to solve each individual side length of that triangle. Here's an example of how we can use that. Professor Axler asks you to find all three angles of the triangle shown in this triangle, where you have a side lengths of 6, 5, and 7. Well, using the law of cosines, if I'm going to choose this side to be my C side, and I'm going to choose this guy to be my A side and B side, because they have to be opposite those angles. That's how I can identify the side lengths. So essentially in this case, I'm going to have my 6 squared is equivalent to my 5 squared plus 7 squared minus 2 times 5 times 7 and cosine of C. This is going to help me find this angle right here, help me find that C angle. And after going through my math, I'm left with a value of 19 over 35 equals cosine of C. And this of course implies that the arc's cosine or inverse cosine of 19 over 35 will give me my value of the side length, will give me my C value, and that is approximately 0.997 radians. Or if you change to degrees, it's roughly 57.1 degrees. And to solve the other angles, I'm just going to use my identities, my other laws of cosines identities, to solve those values. So in this example, we're asked to find the length of all three sides of a triangle, this particular triangle. So we know obviously the side opposite of C, this is going to be my angle C. So going through, you know that C squared is equivalent to 3 squared plus 5 squared minus 2 times 3 times 5 times the cosine of 40 degrees. So going through that, we know that C squared is equivalent to 9 plus 25 minus 30 times the cosine of 40 degrees. And since this is C squared, I need to take a square root of both sides, so I'm left with C is equivalent to 34 minus 30 cosine of 40 degrees, all under the radical. And after using the decimal approximation, that's going to come out to being roughly 3.32. So this side length here has a value of 3.32. And that's how we utilize the sign of cosines. Hope this helps, and remember, come visit ISOmath for all your math needs, and we hope to see you again in the future. See you soon.